Without further waiting, I will just start with the topic for today, which is our refrigeration dryers. So let's have a short look at the agenda for today. We will start with a short introduction and also a dryer type comparison, just a short one. On point 2, we will have a look at the actual object of desire for today, which is our refrigerant dryers. So here we will take a detailed look of how the dryer works and also talk about the internal design and clarify how the air actually becomes dry. We will also explicitly separate the path of the air and the path of the refrigerant inside the dryer. We will then briefly discuss the naming option, naming of the DRYPOINT RA series, and also talk about available options and versions of the dryers. In the fourth point, we will look at how to select how energy saving can be done with refrigerant dryers. So we will talk about the Eco series and see where the difference is between the different types of energy saving dryers. And in the last point, point number 5, we will talk about sizing. So we will do a little example about how to select the dryer for the correct size. And we will also see how to use the correction factors in the correct way. So how you work with the price list to select the correct dryer. And without further waiting interruption, let's just start with point 1, which is the introduction with a short dryer type comparison. So the big question that I would like to ask here right at the beginning is, why is compressed air drying so important? For this, I would like to briefly highlight what would happen if we would not have a dryer in our compressed air system. In my small sketch down here on this slide, you can see a compressor, a vessel or receiver, and at the right end, symbolically shown components of the pneumatic system, such as valves, and of course the application itself. Here, for example, this application could be the blow molding or filling of a PET bottle. In step 1, of course, air is sucked in and is compressed by the compressor. In doing so, the compressor naturally compresses everything it sucks in, also particles and vapor, both water and oil vapor. The same amount of aerosols and particles, which do not cause us any problems in the ambient air or are not even noticed by us, quickly become our problem in a compressed air system, compressed to many times the ambient pressure, because we still have the same amount of aerosols, vapor and particles, but in a much smaller volume of air. As we now do not treat this compressed air, the oil and water vapors will naturally condense as the air cools down in the pipes and vessel, and therefore droplets and liquid water will occur. This can lead to corrosion in the pipes and of course in the compressed air receiver. If the compressed air system corrodes, it will dissolve from the inside and ever larger particles like rust will be carried into the compressed air system. The consequences are clear. Damage to the compressed air system itself, i.e. to the pipes and to other components like the vessel, but also damage to the pneumatics. And finally, of course, contamination of the end product, and thus loss of quality or even production standstill as a worst case scenario. By the way, it should be mentioned that in our example, which is shown here, not only the drying, but also the filtration is completely missing. As a result, the pneumatics and the end product are of course not only stressed by the constant process of condensation and corrosion, but damage can also occur through the unrestricted influence of all the particles that are sucked in by the compressor. So filtration is of course just as important for a compressed air system as drying is. Therefore, the reasons for implementing filtration and drying are obvious, especially in our today's case for compressed air dryers. First of all, process safety is guaranteed. This means no loss of productivity due to negative influences of the ambient air and no standstill of the production. On the other hand, of course, cost savings. Even though a dryer is of course an investment in the first place, the correct use of drying will of course extend the lifetime of all the components in the compressed air system by a considerable margin. This saves the need for regular new purchases or constant maintenance. And last but not least, of course, the quality of the final product. It is not only very expensive to be unable to sell whole batches of products due to problems with the compressed air system. More importantly, once the customer confidence in a product is destroyed, it is very likely that customers will turn away from the company and or the product. So it should be clear, compressed air treatment by compressed air dryers is essential and unavoidable. In order to avoid all these negative effects that I just mentioned, we therefore need one or maybe even more dryers in our compressed air system. For this purpose, we have different methods of drying available. For example, the membrane dryer, whether it is the standard membrane dryer or the controlled eco version. Or adsorption dryers of different series, depending on the required volume flow and size. Or simply the refrigeration dryer that we would like to talk and take a closer look at today. And even if today is all about this one last dryer, in my opinion, it makes sense to briefly compare different dryers with regard to important criteria in order to determine the preferred area of application of the refrigeration dryers. I have brought this, I have brought this overview with me. And even if it seems a bit confusing at first sight, it will quickly become a clear illustration as soon as it is clear which aspects are compared here. Indeed, the x-axis represents the volume flow, from left to right increasing in size. And the y-axis represents the dew points at the outlet of the dryer, which are possible with the respective drying method. These are compared with membrane dryers, known to us as DRYPOINT M, which you can see here in this, well, let me stop my laser pointer, there it is, which you can see here, DRYPOINT M. Then also we have the adsorption dryers, which is in our case DRYPOINT AC, which is here. These are the cold regenerated. Then we have the EverDries, which are the warm regenerated adsorption dryers. And in the end, we also have in our portfolio the refrigeration dryers, which are DRYPOINT R. And this is this blue square over here. So the first thing to notice is the refrigeration dryer is relatively limited in terms of its achievable dew points. So while membrane dryers, depending on the inlet of conditions of course, can cover a wide dew point range, and adsorption dryers can reach much lower dew points, the refrigeration dryer is limited to PDP, so to pressure dew points in the range of just over 0 degrees Celsius to about 10 to 15 degrees Celsius. So why is the refrigeration dryer the most widely used dryer method of all? Quite simply, a refrigeration dryer offers stable drying performance from small to very large volume flows, and this at relatively low cost. While a membrane dryer is more of an point of use dryer, which works best with smaller volume flows of individual applications with higher quality requirements, a refrigeration dryer is perfectly suited to be used in a central treatment system, providing a sufficient degree of drying for most compressed air applications. Of course, an absorption dryer can reach way lower dew points than a fridge dryer, but more complex technology is, of course, often more expensive and maintenance intensive, and in most cases, such dry air is simply not necessary. So therefore, we can say in about 80% of all applications, refrigeration dryers are sufficient for compressed air drying. And what application are these? These are, for example, applications such as those in our own production. So when only compressed air-driven tools are required, such as screwdrivers, grinding machines, or similar. Also for simple painting and priming work, the refrigerant dryer can also be sufficient. For example, if it is only about applying coatings and not necessarily about an optimal surface appearance. So in the end, the refrigeration dryer fits into almost all workshops, also into craft businesses and industrial companies. As the most basic form of general treatment or pre-drying, simply everywhere where the quality class 242, also called general working air, is sufficient for the application. And with that, we are already through with our little introduction and comparison. And if there are or were no questions yet, we could now move on to the second point of the agenda and deal with the layout and function of the refrigeration dryers in detail. So Mark, were there any?
Patrick, at the current stage there are no questions, so you can go ahead with your presentation.
Thank you, Mark. Then this is exactly what we're going to do. So second topic, as mentioned, layout and functioning principle of the dryer. So how does the compressed air become dry, and the path of the air versus the path of the refrigerant. As in almost all our webinars, we at the BQ Education Center never get tired of pointing out that we have a lot of very good videos on our BQ Technologies YouTube channel about the functionality of our products. This also applies for the refrigeration dryer. Of course, we can also use this nice fact in our trainings and also in today's webinar. And therefore, we will now go through the basic function of the RA with screenshots from our YouTube video. It should be noted that even though the title of the YouTube video mentions RA Eco, it is nevertheless to a large extent also applicable for the standard dryers and not energy-saving dryers, and only deals with the operation of the energy-saving models at the end of the video. So yes, and this, what you can see here on the picture, this is what they look like, the refrigerant dryers. Of course, they differ a little bit in shape and color, of course, depending on the company where you buy it from. But in the end, they have one thing in common. From the outside, there's not much to see, and there's also not much to do on a refrigeration dryer. In the end, it's always just a big box with two connected compressed air lines and a control unit at the front. So from the outside, this is already the most important difference between the refrigeration dryers, this control unit. So depending on the model and size of the dryer, we use different control units with different functionalities. You can already see here in this picture that the bigger dryer has a different control unit with a small display compared to a smaller dryer. So normally, like I said, larger dryers have more extensive controls with more functions or different displays. And this is simply due to economic efficiency. The refrigerant dryer market is very competitive. So smaller dryers usually have simpler controllers just to keep the price of the dryer down. We will see a few more details about this during the webinar when it's going on. So as I already said, the main components of the refrigeration dryer are not visible from the outside. So now we take a look inside the dryers. The components inside the refrigeration dryer look somehow like this screenshot from the video. Depending on the size and equipment of the dryer or options that it has, components can of course be different. However, it is important to note that in the refrigeration dryer, there are two separate systems that only cross over each other at one point. On one hand, we have the path of the air through the dryer. Here you can see on the right side the heat exchanger, the so-called evaporator. The path of the compressed air through the refrigeration dryer is completely limited to this one component. In addition to the path of the air, there's of course the cycle of the refrigerant in the dryer. This circuit contains much more components, some of which can be seen here. In the following, I would like to take a closer look at these two paths and thus shed some light on how the dryer works. For this purpose, we will look at a diagram that shows the layout of the refrigeration dryer in a little bit simplified form. So here, the most important components of the refrigerant dryer are shown. So on the left, we have the heat exchanger. I use my laser pointer again. Here we have the heat exchanger that I just mentioned, the evaporator, and that is connected to the Bicomat. On top, we have the refrigerant compressor. On the right, we have another heat exchanger with a fan on it, at least as long as it is an air-cooled version, and this is the so-called condenser. And below here, in a standard dryer, we have the capillary tube, and shown here, as it is an eco dryer in the video, as I already told you, it is an electronic valve, but it has the same function as the capillary tube on a standard dryer. So First, we will look at the path of the air through the dryer and clarify how the air actually becomes dry. So the evaporator is made of aluminum or steel, and this is depending on the model of the dryer, but it always has the same important components. So the compressed air lines for compressed air inlet and outlet are of course connected to the evaporator, which are shown here above. So from here we have the inlet and here we have the outlet. Inlet and outlet are chosen as large as possible to keep the differential pressure of the dryer as low as possible. So after entering the dryer, the airflow follows the force of gravity, which assists the separation of water, which then condenses out during the cooling phase and therefore reaches the drain very easily. So furthermore, it has a air-to-air heat exchanger. It also has a air-to-refrigerant heat exchanger. And the connection to the condensate drain, of course, which is in our case always a Becomat. So with all the refrigerant dryers from Beco Technology, you always also have the Becomat in here. The air to refrigerant heat exchanger is also the only place in the complete refrigeration dryer where the refrigerant and the compressed air paths cross each other. But we are going to see this in a minute when we have a look at the function in detail. So how does the compressed air become dry? It is important to know that the warmer the air is, the more water it can carry in the form of water vapor in this case. So of course, the same applies the other way around. The colder the air is, the less water vapor it can carry. The refrigeration dryer just makes use of this principle. So how exactly is what we will find out on the next slides. Yeah, there it is. So after the air enters the dryer, it is first pre-cooled in the air-to-air heat exchanger by the outgoing and countercurrently flowing cold, very cold compressed air that leaves the dryer. This increases the efficiency of the dryer and reduces energy consumption. After pre-cooling in the air-to-air heat exchanger, the next thing the air passes through is the air-to-refrigerant heat exchanger. So both ways or both circuits naturally remain independent from each other and only exchange heat energy. Compressed air is here cooled down to about 3 degrees Celsius by the refrigerant. And vice versa, the refrigerant absorbs the heat energy of the compressed air and thus heats up. The refrigerant also changes its state from liquid to gaseous, which means it evaporates. And this is also where the name of this component of the refrigeration dryer comes from, because it is called the evaporator, because the refrigerant evaporates. As already mentioned, cold air can carry less water and less water vapor. So for this purpose, we have tables which show exactly how many grams of water the air can absorb at a certain temperature. So after compressed air now is cooled down to about 3 degrees Celsius, air can only carry about 6 grams of water vapor per cubic meter. Any water vapor that was previously contained in the air and that was contained more in the air is now condensed out by the cooling process and is then led to the condensate drain as water droplets. So often when we ask the question, where does the air get dry? We hear the answer that it is at this point because all the excess water vapor has now condensed out. But is this really true? Does the air get dry? So to do this, one must remember when air is considered dry. The whole thing is an interaction of temperature and humidity, and thus the dew point. It is not important which dew point we have, but how high the relative humidity is. In our example, the air has now eliminated any excess water and contains only about the 6 grams per cubic meter water vapor. But the air is also very cold, namely these 3 degrees Celsius. And therefore, with this amount of water vapor in the air at 3 degrees Celsius, we are at our maximum absorption capacity for water. This means that the air is saturated or has 100% relative humidity. And thus, the air is of course everything but not dry at all. So after the relative humidity is now at 100% at the bottom of the dryer or at the bottom of the heat exchanger, the air is saturated. And the air is now guided once more over the air-to-air heat exchanger on its way out of the evaporator. And here, the actual drying process takes place. As I mentioned before, the incoming warm air is pre-cooled by the outgoing cold air. But it is also the same case vice versa. So the outgoing air is reheated, and that is the key. By warming the air, it can carry more water vapor again, and thus the relative humidity decreases. The delta T, so the difference in temperature between compressed air inlet and outlet, differs in size of the different dryers, because different dryers have different sizes and heat exchangers, and therefore we have different differences in temperature. But as general, we can say it is about 7 to 10 degrees Celsius. So let's say 7 for here. So depending on the size of the heat exchanger, this differs. If the air enters the dryer at 35 degrees Celsius and it leaves it again at approximately 28 degrees Celsius, as you can see in the table, the air can now again carry approximately 28 grams of cubic meters of water vapor. But it actually only contains 6 grams of per cubic meter water vapor because it was cooled down to 3 degrees before. So now it has a relative humidity of approximately 20%. 6 grams of cubic meter actual water load in the water, 28 degrees Celsius temperature of the air, and therefore lower relative humidity of approximately 20%. And now the air is dry. Okay. Yeah. Then we have now examined the path of the air in the refrigeration dryer. A key point in drying the air was that the refrigerant is able to cool the air down to about 3 degrees, which ultimately creates the dew point, which happens here in the air to refrigerant heat exchanger. So let's also take a look at what the refrigerant circuit looks like. I already named the main components a few slides before. So the refrigerant flows back and forth between these components in a circuit or in a closed loop, however you like. To explain this cycle, we have to start at a certain point. So for example, here, directly behind the evaporator. So here the air has a pressure of roughly 2 bar, 5 degrees Celsius, and a state and a gaseous state. And it just left the evaporator. So from here, the refrigerant is sucked into the compressor. So what does the compressor do? The compressor, of course, compresses the refrigerant. Compression always means two things. On one hand, the pressure increases, but pressure increase and compression also means temperature increases. So when the refrigerant leaves the compressor here, we will be at around 10 bar and 50 degrees Celsius. So we also had a huge increase in temperature, but still the refrigerant is in a gaseous state. So after the refrigerant or the compressor, the refrigerant enters another heat exchanger here on the right. This heat exchanger is called condenser because here the refrigerant condenses from gaseous to liquid just because its temperature drops. This heat exchanger is also equipped with a fan or ventilator, which you can see back here. At least if the dryer is a air-cooled version, then you will have this fan. This fan just increases the cooling performance of the heat exchanger. And when it leaves this heat exchanger, we are still on the high pressure side, so this didn't change anything in pressure, but the temperature dropped slightly, and therefore we went from gaseous to liquid. Now the last part, or the last important part that changes something on the refrigerant, is normally the capillary tube, or here in the eco dryers it is this electronical valve. So the capillary tube creates another cooling effect through expansion because of pressure drop. And this pressure drop is caused by length and narrow diameter. Yeah? And because of this, pressure drop means always we lose pressure, and expansion always means cooling. Exactly the counter effect to temperature increase when you compress something. So behind the capillary tube now, we are at 2 bar, and now roughly 2 degrees Celsius, and still liquid, of course, because we only changed the temperature, but we didn't rose it. So after all this, of course, we do not only have these 4 components in the refrigerant circuit. These are just the components that are responsible for the major changes in pressure and temperature of the refrigerant. So besides these components, we also have control and safety devices in the loop. So let's take a look at these on the next slide. First, let's complete the refrigerant circuit with all important components, and then let's talk about their function. So we had the evaporator on the left, we had the compressor on top, the refrigerant compressor, we had the condenser with a fan or ventilator on the right side, and down here we had the capillary tube, and then the loop is closed. So now we can already see we have a few new devices in here. So let's start with the devices that actually control the refrigeration circuit. So on one hand, we have the pressure switch over here. Pressure switch for the ventilator of the condenser. This is called PV. So depending on the pressure inside the refrigeration circuit, this switch shuts the ventilator on or off and can therefore increase or decrease the cooling performance. So this is just one way to control the temperature in the whole circuit. Yeah. So if the pressure is too high or too low, this shuts this on or turns the fan on or off, and therefore we have more or less cooling power. So this pressure switch is one controlling device that we have in our refrigeration circuit. And on the other hand, we have the hot gas bypass valve. And this with all its connections, which means we have a connection to the outlet of the refrigerant compressor. We have a connection to the inlet of the compressor, which is the suction line. Then again, we have a connection number 3 here, which is just a pressure compensation for a smoother controlling of the whole circle. And on the 4th connection, we have a temperature probe, which is actually filled with gas. So what does the hot gas bypass valve do? The hot gas bypass valve, let's say, measures, or it actually feels the temperature here on the inlet of the evaporator, exactly where we should have our 2 or 3 degrees to create a certain dew point. So depending on the temperature here at the evaporator, the gas inside this tube here expands or contracts. When this gas expands or contracts, it opens or closes the hot gas bypass valve. And when it opens this valve, what happens is we open a bypass to the actual refrigerant circle so that hot refrigerant from behind the compressor can pass through to the front of the compressor. This is what the hot gas bypass valve does. So here this pressure compensation just smoothens the regulation of it, but in the end it detects the temperature here and therefore controls how much hot refrigerant can flow to the front side of the compressor. So why is that? This just keeps the evaporation pressure and the evaporation temperature constant in the whole circuit. So for example, if the dryer has partial load, so like 20%, 50% or whatever, and there's not much compressed air flowing through here, then we do not have enough heat energy to reheat the refrigerant. Then the refrigerant will be too cold when leaving the evaporator, and so the whole circle or the whole circuit will get too cold. And if it gets too cold, we have the chance that we get freezing down here on the inlet to the evaporator. And if we have freezing here or temperatures below 0, then of course the condensate that occurs in the compressed air system could freeze and block the evaporator. That's what we do not want. So for example, if we have a low load or partial load and we do not have enough heat energy here, then the hot gas bypass valve opens and the whole temperature in the whole circuit rises up again because we put hot refrigerant in front of the compressor and therefore get the temperature up in the complete circuit. This is actually what the hot gas bypass valve does. So these two, the hot gas bypass valve and the pressure switch, are the two main control devices inside the dryer. So both of these are the reason that the refrigerant reaches the low temperature that it is necessary to cool the air down, but at the same time prevent it from getting too cold to prevent freezing in the evaporator. So these two control the whole cycle. But then again, we have some safety devices in the loop. These are the TS, the temperature switch, HPS, which is high pressure switch, and LPS, which is low pressure switch. So All these three devices, these three safety devices, are pure, let's say, luxury devices, and they are not necessary for controlling the actual system. So they are only for safety and more or less luxury, and they are only available in starting from certain sizes of dryers. So the temperature switch and the high pressure switch more or less prevent the compressor from breaking down, and therefore they reduce maintenance intervals. For example, if the filter is blocked or if the condenser here is blocked, then of course the compressor would work against the pressure and would more or less get broken after some time. This is detected by the high pressure switch and it would shut all the thing off. So that's what happens when the high pressure switch trips. The low pressure switch could drip because of leakage in the refrigeration circuit. So as soon as we have a leakage, small or big, whatever it is, we lose refrigerant and therefore the pressure in the whole system gets lost. And as soon as the pressure gets lost, this switch trips, and then everyone knows, okay, we should have a leakage over here, for example. All of these, at least the temperature switch and the high pressure switch, can be resetted by the customers themselves, except the low pressure switch. So if the low pressure switch trips, then you need a service technician to get it running again, because then you have to check for leakages. And if refrigerant leaks out to the ambient, that's of course very bad for the environment. So this is why only a service technician can reset this one. Okay, let's have a short summary on the layout and functioning principle. So as I said, standard in all RA dryers is the pressure switch, which we have here again, and the hot gas bypass valve. By the way, this is the drawing or the scheme as it is in the user manual. We just had it a little bit more easy in our slides before. So what you can also see here is that something I want to mention, the switches, so the pressure switch and also the temperature and low and high pressure switches, they are not situated directly in the refrigerant line. They are situated at some point inside the housing of the dryer and are then connected to the certain measuring points in the refrigerant line. Yeah, but they do not actually sit here. This was only for simplified reasons in the post slide. So standard beginning from the RA330 series, we have the temperature switch as first, let's say, luxury element. And then from 490 and upwards, we also get the high pressure and low pressure switch. And then beginning from the bigger dryers, bigger than 1000 cubic meters per hour, we have different compressors in the refrigerant circuit, like scroll compressors. Then we have the so-called crankcase heater. What does that mean? During still stand of the system, yeah, which means cooling down, the oil of the compressor can be mixed with the refrigerant, and that would lead to irregular flow or so-called hydraulic shocks. And the heater just prevents this effect. Yeah, it keeps the temperature stable and therefore no mixing of refrigerant and compressor oil. Yeah, so this is what it has. And also the bigger size dryers have an advanced fan control. And here we are speaking of the fan of the condenser here on the right. So this pressure switch normally can only do on or off for the switch. But in the bigger size dryers, it can also run with 50%. So depending on the size of the dryer, of course, there are different control units used, but that would go beyond the scope of this webinar today because there are multiple control units in use in our dryers. For this, you can also have a look in the manual, for example. But for the sake of simplicity for now, let's just say larger dryers often have more extensive controls with more or different functions. And this is just due to price of the dryers to remain competitive. So yeah, that would be the place, Mark, where I ask you again if there are any questions, and if not, we could directly hop on to the third part of today's agenda, which is the portfolio.
Thanks for this interesting part, Patrick, this part of the presentation. I'm really looking forward to the next part, to the third part. But yes, we received a question from the audience, and it's regarding the working pressure. So the question is why the working pressure is only 16 bar, or why the working pressure of 16 bar is only available for the smaller units. For bigger, we have only 14 bars. And the question is, are these 2 bars really so difficult to achieve? Or rather, is it that 15 or even 15 or 16 bars are so dangerous for the heat exchanger? So there are no further questions at the current stage. So please go ahead, Patrick, with the third part with the portfolio.
Okay, then as I said, let's directly hop into it. So portfolio or refrigerant dryer series. What series do we have? It's just a very small overview over everything. So of course we have the standard series. We already talked about it or heard it in the past few slides. DRYPOINT RA standard series, which just means standard series. We have a constant pressure dew point output of somehow 3 degrees Celsius. Again, of course, depending on the selection and sizing. But we just have constant pressure dew point. These are available from very small to very high volume flows. Then again, we have the DRYPOINT RA Eco series, which is the energy saving dryers. The energy saving dryers are available with two different methods of energy saving, which is on one hand the cycling principle and on the other hand the VSD, which is variable speed drive, but we will see how this works in the next point of the agenda. So the third part thing we have is the RA high temperature, which is just an RA dryer with a cooler in front and also with a clear point filter in front, so that maximum inlet temperatures are possible to go up to 100 degrees Celsius. And in the end, we also have the RSHP, which is the high pressure dryer with a stainless steel heat exchanger, which is then suitable for max pressures of 45 and 50 bar. I think we will hear some more information about some of these when we have a look at the options and the naming. So this is just the standard series that we have. And also this is only speaking of our European market. In our worldwide portfolio, we also have some other dryers, especially for the Asian market and so on. We have some tropical dryers and classic dryers and whatsoever. So this is just an example of what we have. Depending on where you are in the world or where you live, then we maybe have some other dryers to offer. Nevertheless, which actual dryer series you have, we have some options for all of these that apply to all of these. And these options are, on one hand, we can also deliver the dryers as WC, which is water cooled. I already talked about it before when we had a look at the refrigeration circuit. On the right side, we had the condenser with the ventilator behind. So this is an air-cooled version. If you have the water-cooled version, then this is the condenser over here, and it just has two connections for cooling water, and then you can cool your refrigeration circuit with cooling water instead of air. Then again, we have this in a little bit more, let's say special version, the water cooling, which is the TBH or SVC, which stands for seawater cooled and tube bundle heat exchanger. This just means you can see it down here. The heat exchanger on the right, the condenser, is a bundle of tubes, literally, that's why its name is like this, which is lying here on the right of the dryer. And the difference between the tube bundle heat exchanger and the normal plate heat exchanger is that the space inside the heat exchanger is a lot larger, or you have more space for particles and so on running through the heat exchanger. This especially needs to be taken into account when you have surroundings with like a lot of particles in the surroundings, or for example seawater with salt and particles in it, and as soon as you have this different water, this particularly filled water, then you need a heat exchanger that has bigger space between the plates and therefore does not block. So this is just a heat exchanger that doesn't block as easy as the plate heat exchanger. Then we have the TAC option. TAC stands for treatment anti-corrosion. You can see these here on the right. So this does not mean, as some people think, that we have some coating inside the compressed air line so that you can use more aggressive compressed air or can flow more aggressive compressed air through it. These coatings are just on the outside of the components in the dryer. So for example, the pressure switches, the pipings, the compressor and all this, these have a coating on it. And this is just a coating for industrial environments with aggressive media in the ambient air. So this just extends the lifetime of the dryer by a multiple as soon as you have aggressive media in the ambient air. This, for example, applies for the chemical industry, the agricultural industry, and again, salty environments like sea air. And then again, the last one is the oil-free version, of course. So oil-free just means that you do not contaminate your compressed air system downstream of oil-free treatment. So if you have, for example, an activated carbon tower installed or catalytic converter or whatever you have, everything behind this treatment needs to be oil-free. And this is what this dryer has, so you do not contaminate your system. Yeah, and these are actually the main options that we have. So how about the naming of these products when we put the versions or the series from the beginning together with these options? So let's do this just with a quick example. So for example, DRYPOINT RA 1300 AC THC. DRYPOINT is always the protected brand name of Beko for our compressed air dryers. The direct next letter that you get after DRYPOINT then tells you something about the drying technology, which is R for the refrigerant dryers, AC for the adsorption dryers cold regenerated, or M for the membrane dryers. Afterwards, the second letter, this is special for the refrigerant dryers. This just tells you which type of heat exchanger you have. If it is an RA dryer, you have an aluminum heat exchanger, which means the evaporator, so the heat exchanger for the compressed air. And if it is an S, then you have a stainless steel heat exchanger. The number afterwards is just the volume flow in cubic meters per hour, so that the dryer is able to treat. And then again, we have the cooling medium, which is AC for air-cooled, WC for water-cooled, or SWC for the seawater-cooled version, which is then also again complying to TBH, which means tube bundle heat exchanger. And the last thing that is on the naming is the options. Then you can see if you have TAC, so the anti-corrosion treatment, the tube bundle heat exchanger, or the oil-free versions. And this is actually everything you can say about our portfolio, at least the simple steps. Of course, in some cases, we also offer options like different power supplies or different colors or whatever, but then this only depends if you want to buy enough of the dryers. But for standard, these are the versions and series and options that we have. So, Mark, any questions? If not, then we are already at the point of sizing and selecting the correct dryer.
So we've got no questions so far, so please go ahead, Patrick.
Perfect. Then we are also pretty good in time. As I said, all of us want to do something today afterwards, so we do not want to take you too much of your time. So sizing. Oh, sorry. We're not at the last point. I just forgot one. We are still at energy saving dryers, but still we are very good in time. So energy saving refrigeration dryers. This was the point I missed. So why are energy efficient dryers so interesting? This is the question that you can see up here. The gray area in this scale is just an example for a compressed air demand. You can see here on the side, compressed air demand on the right. On the left, you can see condensed amount of water. You will see what this means in a minute. So a dryer is normally sized or selected for worst case conditions. So also here in this case for the maximum. So here, these two small peaks that we have to select the dryer that is able to treat the load at these two peaks here. But the workload of a refrigerant dryer does not only depend on the height of the compressed air volume flow that needs to be dried. In fact, the workload on the dryer also depends on how much water the incoming compressed air carries with it. And as we said before, the water load of the compressed air increases with rising temperature. So naturally, this plays a major role, especially in the difference between summer and vice versa, the difference in winter. So due to the wide volume flow and temperature range, refrigeration dryers typically operate all year around in a very wide load range, so from approximately 0 to 100%. So let's make this topic even more clear. So it says here technical dimensioning based on worst case. So technical dimensioning of a dryer is always based on worst case conditions. That means we have to select the dryer for the maximum load that can occur, so for the maximum volume flow. So we would assume, like it is shown here, that we have a continuously full load of volume flow. Then again, you also select the dryer for the maximum inlet temperature, the maximum ambient temperature, and the minimum operating pressure, because these are the worst case values. The higher the temperature or the lower the pressure, the bigger the volume is that the dryer needs to be able to treat. Yeah, that's why we have to choose all these values. But again, all these are worst case conditions. So, but is this the case all day and all night long? Of course not. In reality, it looks a little bit different. So normally, it's just pretty seldom that these factors are at their worst values all at once. So therefore, the dryer doesn't have to run on full load all the time. And this is where we have our saving potential. As you can see here, the actual situation of the application is different. So normally in every company, we have a fluctuating compressed air profile or fluctuating demand in compressed air. And then again, only 20 to 30% of the year or the whole operating time of the dryer, we have this maximum inlet temperature and maximum ambient temperature. Of course, today we have an international webinar. This again depends on the regional and seasonal conditions in your country. At least here in Germany, we have very cold winters, or at least cold winters and hot summers. So we have very big differences between summer and winter, and therefore these temperatures or these maximum inlet temperatures only apply in a short period of the year. Maybe it's a little bit different in some countries of Asia where you have high temperatures all year round, but as I said, it depends. But still, you also have fluctuation in pressure in your compressed air system all the time. We here at BICO in our production, we also differ between 9 and 10 bar somewhere around. So pressure changes from time to time. And that is the point where, just as I said, where the actual saving potential is there. As soon as you do not have all these worst case conditions at the same time, you can save money if the dryer is not running at full load. So what can we do to achieve that the dryer is not running at full load all the time? Let's have a look on the different energy saving options we have. So let's assume that this red line here is a compressed air demand that we have. Yeah, just over time, a certain amount from 0 to 100%. Then again, you can read here, DRYPOINT RA, which is the standard series, would have a power consumption that looks like this. So we would have a stable power consumption because a normal standard dryer that delivers a stable dew point output also has a very stable power consumption at 100%. For the DRYPOINT RA cycling, this looks a little bit different. So you can already see here, and I mentioned it in the series that we have, we here at BICO, we use two different techniques to save energy. On one hand, we have the cycling technology for the smaller dryers, and from a certain size, we have the VSD, which is the variable speed drive, which means we have a frequency controlled dryer. So for a cycling dryer, the energy consumption would look, for example, like this. So it would run at 100%, then the demand of compressed air would drop under a certain value, and if the dryer detects that, it just shuts off to 0. So it turns completely off. As soon as the demand rises again, the dryer switches on again, and then you have drying effect with a little delay of dew point, but you have a drying effect. So now you can see here in the red curve that the demand is already decreasing again. But why is the dryer not shutting off? This is just because of the 6 minutes rule. So these 6 minutes are a requirement from the compressor in the refrigeration circuit. It is not allowed to switch off more than 10 times in an hour. And that's where the 6 minutes come from. So in the control unit, so you have these 6 minutes set up. So even if the compressed air demand drops in these 6 minutes, the dryer is not going to shut off. After these 6 minutes are over and the timer delay is over, the dryer detects if there is demand or not. If there's no demand, it switches off. If there would be demand, which is not the case here, it would just run until there's no demand. Yeah. Then again, it is just doing the same vice versa. As soon as demand comes back, dryer switches on. This is just how a cycling dryer works. Now let's have a look at how a VSD dryer works. So a VSD dryer would look somehow like this, the green curve. So the VSD dryer follows the actual demand on compressed air pretty good. This is also because the VSD dryer knows more values than the actual cycling dryers. So the cycling dryers are only measuring the temperature in the refrigerant circuit, and the VSD dryer is measuring temperature and pressure. And therefore, it has more values to look at, and depending on how fast they change, so fast or slow, we also have a frequency controller in the circuit board, and this frequency controller can just power the refrigerant compressor directly after demand. So the compressor can run at every percentage between 0 and 100% depending on what the frequency controller gives out. So that's why these VSD dryers can very easily follow a fluctuating compressed air demand. So why are RA eco power consumption that you can see over here for the VSD dryers over 100%, you could ask? So this is just because of the frequency converter. Yeah. So the frequency converter is of course a device that is not included in the RA or RA cycling dryers, and that needs power consumption. So as soon as a VSD dryer is running at 100% load, you have to use 100% load of the dryer, and then again add the certain amount of energy that the frequency controller needs, or frequency converter. So that's why we go over 100% here. But then again, frequency controlled dryers are best used when you have fluctuating dew point conditions, fluctuating compressed air demand, and therefore you will not have a continuously running dryer most of the time. So what does this mean for dew point? Here you can see again on the top the curves we just talked about. Now we want to set these into relation to the pressure dew point that the actual dryer gives out. So for a standard RA dryer or a standard fridge dryer in general, the dew point curve would somehow look like this in most cases. So it fluctuates around a certain value that is given by the manufacturer. So in our case, the dryers are selected for 3 degrees. Of course, you also can select these dryers for 7 or 10 degrees, also with the prices and correction factors, but we're going to see this in a minute. So the dryer is going to fluctuate a little bit around these dew points. So for the cycling dryers, this is a different story, because then you definitely have way higher dew points, especially after the dryer shut off. So as the dryer shuts off, of course, you don't have any cooling effect in the refrigerant cycle anymore. When you don't have a cooling effect in refrigerant cycle circuit, these temperatures rise in the circuit, and then again, after switching on the dryer, you do not have a full drying performance after switching it on. And that is why the dew point at the outlet of the dryer normally rises a little bit higher than the actual value that it is selected for. So this curve is also then again pretty nice. So 7 degrees is also a pretty nice value, but to be honest, and we are always honest, we also see it in the dryers in our showroom. These cycling dryers can also easily go up to 10 degrees after they shut off and go on again. So this is nothing special. But then again, this is also not a problem at all, as long as the application does not need a certain dew point. And that is most of the time the case when you use a fridge dryer. Then the application, if it doesn't need a certain dew point and just needs dry air, then 10 degrees Celsius dew point is still enough to have dry air, as long as your ambient temperature is not lower than 10 degrees. So that's not a problem. For VSD dryers, the curve is more or less looking like the curve for a standard dryer. So you have a pretty stable dew point. It's just a little bit over the top here in this. You have a pretty stable dew point, but then again, you save a lot of energy while maintaining a stable dew point. Then again, this curve for the VSD dryer is only correct if it runs permanently in frequency control. And this is something I also have to add. So our VSD dryers, the bigger eco dryers, have the option of running in cycling mode. So they can do both. They can do cycling and VSD. So they work in frequency controlled mode as long as there is a certain demand in volume flow. And as soon as this demand drops to a certain level, then the dryer will shut off completely and run in cycling mode, and will then start up again and work in frequency controlled mode as soon as the demand is there again. So VSD dryers can use both. And of course, if the VSD dryer would switch, for example, here into a cycling mode, then the dew point would also rise afterwards. Yeah? But this is just, again, the normal principle of cycling. So let's have a short summary about the energy saving dryers, starting with the cycling dryers and ending with the VSD dryers. So cycling dryers definitely have a higher dew point fluctuation. This is just because, the nature of the dryer. The dryer is a slow reacting system. It is the whole refrigerant circuit is a reacting system that reacts to temperatures, but it is a slow system, so it cannot directly change as soon as a temperature change occurs. That's why you get these higher dew points at the outlet. So you get higher dew points with cycling dryers than with standard dryers. Then again, the energy saving potential is higher during longer periods of no demand. I guess this doesn't need any explanation. As soon as you have one shift or two shift working company, an eco dryer makes totally sense. Also a cycling dryer makes sense because a continuously running dryer would consume its full energy power also overnight or in the shifts where no one is working, and therefore you have always energy savings as soon as you don't have a 3-shift working company. So, but the longer these periods of no demand, the higher the saving potential is. A good place for installation for cycling dryers would be upstream the vessel or the receiver. So why is that? Of course, if you install it upstream the receiver, so before the vessel, it only gets the amount of air that the compressor is delivering. So as soon as the compressor is running, it is delivering its stable amount of air that the compressor is able to produce. And as soon as the compressor switches off, the dryer can also switch off. If you place the cycling dryer behind the vessel and you have a continuous volume flow behind the vessel because all your applications are running all day, then again, you do not have these good, not so good saving potentials with a cycling dryer. So that's why upstream the receiver is a good place for a cycling dryer. For smaller cycling dryers, there is another point that could lead you to buying a cycling dryer. Not only the actual energy savings that you could have, but especially the smaller cycling dryers, as they are pretty achievable or not that high in price. You can use them for the emotional effect, or let's say the green feel of the customer, because we heard it pretty often in the past that some customers just have a very strong environmental awareness and just want to use components that somehow save energy and therefore save the environment. So this is also sometimes a reason why you could want to buy a cycling dryer or an eco dryer in general. So reasonable energy savings are always bigger on bigger dryers, and that's the case why we say VSD dryers or variable speed dryers are only available from a certain size onwards. So as far as I know, from 1300 cubic meters per hour in the actual price list at the moment. So VSD is only for bigger dryers and for fluctuating air demand. Of course, fluctuating air demand, because then you have the highest savings against the cycling or a continuously running dryer. And again, one very good point of the VSD dryers is they can keep dew points stable, same as a standard IRA dryer. So speaking of motivations that you could have to buy an eco dryer, what are the key buying motivations for buying an energy saving dryer? So in our opinion, there are 2 points or 2 key motivations to buy an energy saving dryer. On one hand, this is of course the economic motives. This means reducing running costs, reducing energy costs, reducing maintenance costs, all that. And in some countries, you also have a refund system. So sometimes you can get money back from the government as soon as you use components, whatever it is, that save energy or that save the environment. So economic motives are definitely one thing to look at when you want to buy an eco dryer, or the first motive normally. But then again, in the past, we more or less heard it ever more often that another motivation is emotional motives. So energy saving is not the highest motivation, but still there, but also the company reputation is taken into account. So if the company, as I said before, wants to have a good image and wants to, customers rely on a company that that it has a good image and a good reputation regarding environmental safety, then this can also be a factor regarding buying a energy dryer. So at this point, this is something I just would like to ask you, and this is also very, very fast. I have another poll here, like Mark already said in the beginning. So we have a poll here that just asks you about the energy saving. So I started it right now. You should see it here. Which of the following reasons would most likely lead you to buy an eco dryer? You can also select both. It is just an information for us. Do you think it is only the economic reasons, or is emotional reasons also something that you or some customers of yours came around with and said, I want to have a dryer because of, yeah, company reputation, for example. So then, Mark, were there also any questions, or should we go on with the sizing part, which is the last part for today? And we are pretty good in time, I guess.
So thank you for the comparison of the dryer, the cycling one, the VSD, and the standard DRYPOINT RA. And it seems that you are doing quite a good job because there are no questions at the current stage. So everybody, please feel free to send us your questions during this webinar, and we will try to answer them in the best way we can. But
Okay.
Now I think it's once again your part, Patrick, part number 5, the sizing part.
Okay, then let's just go on with the sizing and selection before we end this short webinar session for today. So sizing, how to use the correction factors. One topic that always is a little bit problematic sometimes, using the price list and using the correction factors. So you can read it up here, important influencing factors for the dimensioning of refrigeration dryers. This is just a screenshot that I made from the price list. So this is what you can see in the price list as soon as you open the pages for the refrigeration dryers. So here we have correction factors, 1 for the operating pressure, 2 for the ambient pressure, and 3 for the inlet temperature. Yeah. And if you like, this is just as you like, you can also select a certain dew point that you that is enough for you. So if you say I do not need 3 degrees, which dryers are made for, you can also say I only want to have 5 or 7, then you also get a correction factor for that. So this is just the view that you have when you look into the price list. But the word correction factor is, let's say, a little bit misleading. So if you hear factor, you could normally think I always have to multiply these with something. In the end, what we want to know is the actual volume flow that either a dryer is able to treat or that my dryer has to be able to treat. These two options is what we have. So it depends on what you're looking at. So if you see it down here, if you have a dryer selected, or even if you have a dryer standing in front of you and you know the size and what it is able to treat, and then you want to know what performance this dryer would deliver under certain circumstances, then you multiply with the correction factors. But as soon as you have the application and want to select a dryer, so you do not have a dryer and you want to select one, you have to divide by the correction factors. That is very important. So selecting or sizing always, dividing by the correction factors. So this means if you want to dimension a refrigeration dryer, this means the volume flow that the dryer is able to treat, which you get from the price list. For example, RA 1300 is able to treat 1300 cubic meters per hour. And then you divide this volume flow by either all the correction factors multiplied, or you divide one after each other. So you take the volume flow divided by 0.86, divided by 0.93, divided by 0.57, whatever it is. This is just the first introduction. For this again, of course, we have an example. Yeah, I think it's always better to do this with an example and see what the actual numbers are or how the actual numbers are used. So let's look at this example. So a customer would like to set up new assembly stations with pneumatic impact wrenches in his factory. He is already our customer and is enthusiastic about our refrigeration dryers since the reliability and lifetime of his compressed air system could be increased enormously. He purchased a brand new compressor for the new assembly station and is now asking for the appropriate refrigeration dryer. Which dryer should we offer? This is just a task that we want to have a look about. Then again, it says here we have assembly stations with pneumatic impact wrenches. So of course we need the data from these impact wrenches. We got these from the customer, which is an operating pressure of 6.3 bar, overpressure, and maximum air requirement per impact wrench, so for everyone, is 600 liters per minute. Or if you more or less like to calculate it in cubic meters per hour, like we do in Germany normally, this would be 36 cubic meters per hour. And we also have the number of assembly places, which is 30. And this is very important because it's not enough to just calculate with the volume flow that you need for one gun if you have 30 assembly places, of course. Then we need some other information because temperatures are also important. So from the customer, we also got these conditions of his compressor and workshop, which means ambient temperature in the compressor room will be 30 degrees for him. And the inlet temperature to the dryer, so the actual compressed air temperature, will be at around 45 degrees Celsius. So now we have all the values that we need. What we now need is the correction factors. So I put the screenshot again up here, which you just saw on the slide before, which is just the output of the actual price list. So we just look into this price list and have a look at the certain correction factors that we need to use. But before we need to calculate the actual volume flow. So 600 liters per minute is, as it is already shown here, 36 cubic meters per hour. And now we have to multiply this with 30 because we need the maximum volume flow. So this means if we have these 36 cubic meters per hour multiplied with 30, we end up with roughly 1080 cubic meters per hour. And that is the volume flow that we need to divide with the correction factors. So as you can see here, we had these 600 liters per minute, as I said. We just converted it to cubic meters per hour, multiplied it with 30, and we end up with 1030 cubic meters per hour of volume flow. So these now are divided by all the correction factors. So 1030 divided by 0.93, which is for 6.3 bar, you can see here. Then divided by 0.95, which is 30 degrees Celsius ambient temperature, which you can see here. Then we had 45 degree inlet temperature, which is 0.68, therefore divided by 0.68. And the customer said, I would like to have the 3 degrees that the dryer is selected for. That's why he uses 1. But you can also leave this away if you use your 1 because you do not have to divide by 1 because it's the same. What you end up with is 1,800 cubic meters per hour, roughly, 1,798. So with this volume flow now, you go into the price list and select the dryer. And for this, we have the RA 1800 AC. So of course, this is very close to its performance limit. So in order to guarantee a stable dew point, we could offer to select a DRYPOINT RA 2200, which is a little bit bigger, but it is a safer option, yeah, because this one is selected on the edge. But then again, remember what we said before. When we were talking about energy saving and when we were talking about ambient conditions and worst case selection, what we just did is we selected all these correction factors and the sizing of the dryer if all this would occur at the same time. So 6.3 bar, lower pressure, high ambient temperature, high inlet temperature, and we want to have 3 degrees in this time. Then this volume flow would be correct. But normally, this is just not the case all at once or all at the same time. And then again, we have to take something else into account. Here, this divides onto 30 assembly places. So if, for example, only 10 of these are running, 10 of them are actually optional or not running all the time, 10 of them running continuously, and another 10 are just left behind in storage, then we do not have these volume flow for all 30 at the same time. And then again, an RA 1800 is fully okay, and you do not have to offer the big one. But as I said, it's always, you have to take a closer look at each case itself. So you cannot say it's always the same. What we can do always the same or always on the right side is use the correction factors how they are supposed to, and then we are normally not doing anything wrong. Because if we use them how they are supposed to, we get a result which is for worst case conditions, and therefore more or less all of the time this is safe. Why do we have to use correction factors actually in the first place? Of course, when we as a manufacturer produce a price list, we have to set this price list up somehow. So we have to set our products up with a certain volume flow that we name in the price list. And for this, we need standard conditions. And these standard conditions for us are just given by the compressed air industry. So in the compressed air industry, standard conditions are 7 bar of pressure. That's why we have here correction factor 1. 25 degree of ambient temperature, correction factor 1, and 35° of inlet temperature, correction factor 1. So these are the standard conditions. So if you look, open our price list or the price list for nearly any competitor, you see the dryers in there and you see which volume flow they are able to treat. And the volume flow that is written there is only available at 7 bar, 35° inlet temperature and 25° ambient temperature. As soon as your values in your application differ from these standard values, then you have to use these correction factors to select the correct size of the dryer. So this is actually how you select the dryer. But then again, every selection, as I said, is a little bit different from the one before. So you could ask the customer some more points. So for example, down here you see further questions to the customer. Is the compressed air system only in the inside of the factory? This is also important to know, at least here in Germany. In wintertime, we will always have freezing here in Germany on the outside. So if the compressed air line that the fridge dryer is connected to, for example, is running in free air between two buildings, then a fridge dryer is not sufficient for drying because we would get freezing in the pipe system outdoors. Then again, does the dew point of 3 degrees Celsius need to be guaranteed? So is air quality actually important? Do you need this 3 degrees? Or are you also okay with 5 or 7? If that's the case, then you could use the correction factor for 5, 7 or 10 degrees. And what would you end up with? Correct, with a smaller dryer. So if you use these correction factors, the only thing you get is a smaller dryer, because then we intend to overdrive the dryer. So to flow a volume flow over the dryer that is actually too high or higher than its nominal volume flow. This does not destroy the dryer. It just decreases its drying performance, and therefore you get worse dew points. And for this we have the correction factor. So if 7 degrees Celsius would be okay, you use this correction factor, then you get a smaller dryer that delivers you 7 degrees Celsius with this higher volume flow. Okay. Then again, you could ask, how much does the ambient temperature fluctuate in the compressor room? Of course, this is also important. Yeah? But as I said, selecting is done to worst case conditions, so it's not that important. Is there a possibility to cool with cooling water? This is definitely very important, because as soon as cooling water is available and the customer is willing to use it, then you have to sell, of course, a WC dryer, which is a water-cooled dryer instead of a air-cooled dryer. So these are just some further questions that you could ask a customer when selecting a fridge dryer.
Okay, great. Thank you, Patrick, for your presentation and for answering all the questions so far. We still have one question left. Maybe we can discuss this question as well. So one of our participants has a customer and he's using a refrigerant dryer with a pressure dew point of 3 degrees Celsius, which is requested. And they noticed that there were condensate appear along the pipe after the compressed air leaves the dryer. So have you an idea what could be the problem, or is it a question we should comment on later on?
Yeah, I mean, condensation normally is a simple physical fact. So condensation happens always then when air cools down to a level where it cannot carry all the water that is still inside, same as in the dryer. So if you, for example, just an example, I do not know any exact temperatures, have 28 degrees of temperature that is going out, compressed air temperature that is going out of the dryer, but around the dryer you have air that maybe is very hot, maybe also in other countries, and you have a lot of water in it, it can definitely happen that because of the cold piping after the after the refrigeration dryer, that you have condensation on the outside. But normally that's not a problem. Of course, it's a problem as soon as the condensation gets rust onto your or corrosion onto your pipe system. But on the outside, it's normally not that bad.
Then this is all we have for today, also from my side. And right now there are no further questions. And I have to say thank you all for joining our today's webinar. So enjoy your day. Bye-bye.
Bye-bye.